In this episode, we're going to get into something which is useful for model trains, and that's lighting using LEDs. Now, since this is an educational course, first of all, I'd like to have us all understand what a diode is, so we're going to discuss that first. Then what a light-emitting diode is, and how to match that with a resistor and why we need to. Then how we can dim these LEDs and how by dimming LEDs and having different intensities and so forth can make our model trains look more realistic. Before I continue, I'd like to explain that I sometimes will, instead of saying LED, I will say LED. Now, I was told that this is improper, that no one says LED, and LED is the proper way to refer to a light-emitting diode. So I did some research and found that older engineers like myself, and for some reason especially mechanical engineers, use the term lead. And since one of my degrees is in mechanical engineering, I've always used that, and therefore I may swap in that term as I go through this, but LED and LED are interchangeable. Now, since this is educational, let's start with what really is a diode. And basically, an ideal diode would be a device that lets current flow in one direction, but not in the other. And if we go back to, in episode 2, we had an analogy with water, and I hope you watched that. And if we go back to that analogy, we find that a diode is like a check valve, and the one I have shown here is would be like a flapper type check valve. And basically, there's a diaphragm that's on a hinge, for example, here, and around the pipe would be this sort of steel seal or stopper. So basically what happens if the water flows in this direction, the flapper is pushed open, and therefore the water will flow through. If the water flows from this direction, it forces the flapper closed, and the water can't flow. And that's the simple analogy of water and current to a diode. There's an electrical analogy for a diode, and that's of an automatic switch. And basically the diode symbol is this type symbol. Now if we put a positive potential across this, positive on this side, negative on this side, the diode acts as a closed switch. If we reverse it and put the negative on this side and the positive on this side, it acts as an open switch. Now, the convention here is the conventional current definitions. I explained that, I think, in the first episode, and I just want to point, and from now on we're going to use those conventional current definition. I just want to point out that it could have been Ben Franklin who got it wrong, but the actual electrons are going in this direction. I don't want to confuse anybody, so I won't point it out again, but this is from now on, and in this case, it is conventional current definitions. So, let's look at what a diode does. If we hook it up sort of in the backwards way with the negative on this side and the positive on this side, as we said, it's like an open switch and nothing happens. If, on the other hand, we would reverse it, now the current can flow, our light bulb would go on, and everything would be fine. If we go back the other way, again, the light bulb would go off, and the circuit would not work. Actual diodes are not perfect, and there is a voltage drop across them. when it's a closed switch, and as a closed switch, a conventional switch, has a voltage drop in it, but it's typically very, very small, tens of millivolts or something, where a diode can have voltage drops of 0.3, even 1 volt, depending on the type. For a silicon diode, it's typically 0.7 volts, and that's what we're going to choose in the discussions going forward. This closed switch voltage, okay, which would be when everything is applied properly and the light is on, is in this diagram, is called the forward biased. The open switch voltage it can be much larger, and it's called the reverse bias. And in actual diodes, if you make this too large, if you apply too large a voltage backwards, it will break down. But so we're talking about small levels here, you know, a few volts. A LED is a diode that, when forward biased, in other words, the current is flowing through it, it will emit light. It's as simple as that. It's a diode that will emit light when the current flows through it. And the symbol is the diode symbol plus these little arrows, which indicate that it's LED. Now, the real advantage to an LED is normal light bulbs convert electricity to heat, and then that heat through that very small coil produces light. A LED converts electricity directly to light, and that makes it much more efficient because you don't have that heat production, and much cooler. If you've ever touched a conventional 100-watt light bulb, it's very, very hot, where LEDs are cool and really only take milliamps, about 20 milliamps typically, of current flowing through them. Now, let's look at a very simple LED circuit, which consists of a power source here, a LED itself, and a resistor. Well, the resistor is called a limiting resistor, a current limiting resistor. And it's not theoretically absolutely necessary, but these LEDs are very sensitive to current. So at our level, I would say, let's just always put this in. If you keep this voltage below the forward bias voltage of the LED, it is possible to run it without that, but these are so sensitive and change with temperature, change with just from LED to LED, that it's best to put this in and limit the current going through it. So the LED itself looks something like this, the ones we're going to use. I think the ones that are in the kit, that if you purchase our kit to do these experiments, they're 5 millimeters. This is a little dome. I think we give you red, green, and clear, or white. The notation on this is the long lead on these LEDs is always the positive side, or which would be this side, and the shorter is the negative, or the cathode. This is called the anode, this is called the cathode, would be on this side. So let's create a circuit. We're actually going to go out and we're going to build this circuit and show you how it works. And then we're actually going to play around with resistance and see what that does to light. Well, the first thing we have to do is determine what should be the resistance. Well, what do we know? We're going to know what the supply voltage is. And in our case, in our experiment, we're going to use the 3 AA batteries, so that would be 4.5 volts. We also have a LED. Now, LED. Well, when you buy your LED, or in our kit, you should be supplied with the forward voltage and a forward current, which is the current that will, sort of the optimal current that will light this the brightest without going over. So we should be supplied these things. So what we need to do is calculate an R, all right? If we look at the circuit, the supply voltage has to be equal to the voltage drop across the resistor and the voltage drop, or this forward voltage, across the LED. So we're given the supply voltage and the forward voltage. If we look at the voltage of the resistor, we can just apply Ohm's law, because we know the current, or the current we want to go through the resistor, is this forward current we want to go through the LED. So if we apply Ohm's law, we find out that the voltage drop across the resistor should equal the forward voltage times the resistance. Now we can just simply plug this back into up here, and we get the following formula. And then in one of the previous episodes, we talked about that we can add the same thing to both sides of the equations, and we can multiply both sides of the equation by the same amount. So if we use and apply those two laws and manipulate this formula, we should be able to come out with the resistance that we need is the supply voltage minus the forward bias, or the forward voltage of this LED, divided by the desired forward current we want through that. And if we apply the values that we're going to be using in our experiment, the 4.5 volts minus the 3 volts of the forward bias of the resistors, the amperage of the LEDs that are supplied in the kit that we're going to be using is 20 milliamps. But remember, to use these formulas, we need to convert that milliamps back to amps. So we put in the 0.02 amps. We solve that, we get 75 ohms would be the sort of the optimal resistance that we want. Now, I went through this simply so that you could understand where these results come from. You can study them. You don't have to remember them. I certainly don't do this every time I want to determine what resistor I should use. If I have a circuit that's got LEDs in it, 1, 2, 3, there are plenty of apps for the cell phone, and I have one on mine, that you just go to. You plug in the supply voltage, the forward voltage, the forward current, and the number of LEDs you have in series, and it will calculate for you the resistance that you should put in that circuit. So that's what I normally do, but like I said, I just wanted to go through this so you can understand where this comes from. Now we're going to go over, and we're actually going to implement this circuit on our breadboard. So what I've done is I've laid out all the parts we'll need for this little experiment. What I have is 7, and these should all be contained in your kit if you purchase our kit. I have 7 white LEDs, and then I have a series of 7 resistors. These resistors go all the way from 75 ohms, which is what we calculated should be the correct value, up to 30k ohms. I have my little 4.5 volt battery pack with 3 batteries. I have my meter, and for that I've clipped on some of these leads, alligator clip leads, and I'll show you what that's for in a second. And then we have our breadboard that's contained in the kit. So the first thing I want to do is I want to
just check one of these resistances. I'm going to check this 75 ohm one, which is a very small one. Now, when you test something that small, the wires in the that you're using will have a resistance. So first I measure those, and it shows about 1.92 ohms is the resistance through our leads and then these little alligator clips. So if I then clip on here, I get 77.6. If I subtract the 2 ohms, I get about 75.6 ohms. So that's pretty good. I think these are 1% resistors, and that's within the 1%. All right, so I'm going to take those off now, these leads. That was just to show you when you're measuring very small ohms, you should find out what the leads are contributing. So I'm going to start by plugging in my battery pack. I'm going to use the negative, will be the blue. Now, if we remember from our other videos, I'm going to move this back here. Hopefully you can still see that. All the positions on this row are connected on this strip. All the positions on this row are connected. And then there's a connection of these 5 holes here. So what I want to do is I want to take a lead. I'm just going to create the basic circuit. Take a lead. The long lead is the positive lead. So I'm going to plug that in up here. Plug the positive lead into the positive side of the battery. And I'll plug it in to the one below. Then I'm not going to cut my leads. Actually, should have put my battery in down here and got that ready to go. So we got power. I didn't want to put that in until I had it connected because I didn't want the wires just flopping around. So I'm going to leave these. I'm not going to cut them. Leave them alone. Since all these on this line are connected, I'm going to plug into there. Then I'm going to plug the other side into the negative. So that will complete our circuit. And our lead lights up as we expect. Let me get that in good there. All right. So that is pretty much the circuit that we had. It's full strength. The lead is full strength. You can see it from the side or the top. So let's look at our voltage drops. The voltage drop across the battery, or the battery is putting out 4.615. Okay, so let's put that in the calculator, 4.615. And the drop across the LED, it said it should be 3 to 3.2, and the forward voltage right now is 3.054. So I'm going to subtract that. And we ought to have a 1.561 drop across our resistor. And within the a thousandths, that's what we've got. We're off by 3 1,000ths. Well, this meter, I'm sure, is good to that. Plus, we have the drops in the connectors and everything else. So everything works. Now, since we know that the drop across this is 1.56, that's what it was calculated to be. And if we divide that by the resistance, which was about 75 ohms, we get that we're running about 20.8 milliamps through that resistor. So everything has worked out well. That's about what we calculated it should be, and that's great. So now what I want to do is I want to reproduce the same circuit. but I'm going to reproduce it, each circuit, with a slightly higher resistance. So I'm going to plug my long lead in here, the down one. I'm going to take my next resistor. This is about double the first resistor. It's actually exactly if you take the spec. And I can see, I'm not sure you'll be able to see, but I can see a slight difference in the power there, but not much. So let's continue on and put our next one in, and this 220 is about 3 times the resistance of the 75 ohms. So let's plug it in and see what happens. And again, I can see, I'm sure the camera might not be able to see, but I can see a slight drop. All right, let's continue on, increasing our voltage as we go, increasing our resistance as we go. Here we have a 1K resistor, so that's what, about 12 times, actually 14 times what the original was. So let's plug that in. And now, hopefully on camera, you can see that it's starting to drop a little more. Let's see what it looks like from the side. All right. We'll continue on. The next is 3.3. Line that up. I'm sure the camera is not showing this as well as when you do the experiment. You'll be able to see. Now I can start to see a significant drop. And if we look at it from the side, hopefully the camera will pick that up a little better. All right, I'm going to add the last two, which is a 10K. And then a 30K. This is our 10K. And that, you can tell a definite difference between there and there. Then I'm going to put in the 30K. And that is quite a bit of drop. And let's look at it from the side. And that's, you can see from the side, I think a little better how it's dropping. The flashing is because the battery isn't connected that well. Now what I'm going to do is I'm going to pull out some of these so that the brightness isn't, hopefully it'll show up a little clearer on camera. If I pull out, say, these, I may pull out that one. So there we have 3 different values increasing. You can see it from the side, definitely. You can see it from the top also, you should be able to. Now, well, what's happening? What's happening is these increased resistors are really cutting down on the current flow through the LED, and therefore it's not producing as much light. We've still reached, we still have enough voltage to pass current, therefore we're above whatever the threshold is for the forward voltage. And I think if we measure, we'll find out that the forward voltage that it's actually seeing here is probably quite a bit less. So I'm gonna put the meter on here, and it is. On this one, we're only seeing about 2.5. On this one, we're seeing our full 3.047. So you can see how the current really is dropping here, and that's why the light is less. So what does this mean to model trains? Well, it basically means that if you want to have a building and you want to have some realism, instead of just always driving your LEDs at the peak value, if you put a resistor, another resistor, or a larger resistor in series with the one that may already be there, you will dim the light. So if you had, like, for example, an apartment building that's upstairs or some store on your layout, you could put little partitions in to block the light between windows, and then have different levels of light coming from each window. You may have a very dim room, you may have a very bright room, you could have bright lights downstairs in the store, so that it just gives some variation. And adding resistor is a very simple way to get that variation and make your model train a little more realistic. Until the next time, thank God for your blessings, and thank the men and women in uniform, the police, fire, military, for your safety. Thank you for watching this video.